Hello, my name is Neil Hansen. I'm a diagnostic radiologist in Omaha, Nebraska. This is the first in a series of physics lectures which I am producing for my residents as well as others to utilize. This first topic for the physics series is the basics of atoms, units, and radiation interactions. I will use poll everywhere for some audience-based interaction. When I give the poll live, I have you enter Neil Hansen 357 into the pollev.com website. However, this is remotely, so if you're watching this via video, then what you can do is I'll give you a URL later on, or within the description for the YouTube video, there's a link for a quiz where you can interact and take questions along with our lecture today. I find it just helps keep people awake and engaged. If you're at least clicking and doing something, taking a guess, testing your knowledge, as we do questions during the lecture. So for this physics didactic curriculum, we are really going to cover lectures that are the topics of the online Radiologic Society of North America modules for radiology residents. You can go to rsna.org to find these modules. There's a series of them. Some of them are quite good. Some of them maybe still need a little bit of work. However, it's basically what this large radiologic body feels that residents need to know to get through physics for their core exam as well as to succeed in life as a radiologist. Some modules are great for first years while others kind of need a little bit of work. So use them as you find them beneficial. We have numerous lectures that are dedicated from our department to this didactic curriculum, and many of their videos will be uploaded as well. In total, there's around 30 lectures. These are offered through this virtual online course now for the first time ever, accelerated by the pandemic, but feel free to use these videos as you see fit. Some, like today's, I'll be just honest, are really just the nuts and bolts of what you need to know to understand physics. They're pretty dry, pretty boring. Not much I can do about the topic material. Others, like the artifact lectures in particular, for every modality, CT, ultrasound, MRI, are much higher yield in terms of what you might see on a core exam or what you might see in real life and have to troubleshoot using your physics knowledge. What are the goals of this curriculum? Well, I want the learner to have a knowledge foundation sufficient to get through the ABR board exam. I want you to have knowledge of physics used in clinical practice, knowledge that you can use when you go out to buy a scanner, be it MRI, CT, or whatever. I want the learner to gain knowledge of the basic physics utilized in clinical and basic science research pertinent to their practice. So when you open up a research article and read about KVP and KVP manipulation, I want you to at least understand the basics of what that means. And I'd like to keep you awake. So again, I would encourage you to take that poll everywhere quiz as you go through this lecture, just to keep you awake, engaged, clicking and doing something. I also frequently try to be funny. It doesn't always succeed, but feel free to make fun of me in the comments section, which I probably will not read. Curriculum. So it continues to evolve over time. This is about the fourth or fifth iteration of the physics curriculum that I've done since I started as an attending in 2013. So also, if you have any suggestions on how to improve this, feel free to contact me. This is way better than what I got. So, you can criticize this all you want. Oh, it's not that good, whatever. I'll tell you, this is better what I got. I felt like I really taught myself physics. A lot of the PhD physicists were really, really, really knowledgeable people that tried to teach me, but none of it was clinically relevant, and it got lost so much in the details that really it didn't help me get through boards. Some topics are hard or boring, and the lectures may reflect that. Especially the nomenclature stuff is particularly rough, but you have to be able to speak intelligently about that. Otherwise, you won't be able to intimidate other people with how smart you are. This is my final used salesman pitch for why you need to learn about physics. We've bought in a lot of equipment at our institution. I've been a part of the search force for this equipment purchasing. And I'll tell you, if you don't have any idea what a detector does or what a CT detector and how it works, you're going to be lost when you meet these salespeople that want to sell you a $2 to $3 million machine. If you don't have the basics down of how images are created and the physics behind image acquisition, you'll never be able to intelligently purchase a piece of equipment that's incredibly expensive, which many of the people watching this video will someday be a part of. You know, no pain, no gain, just like Dwayne "The Rock" Johnson. You know, everyone wants to look like this guy, be able to lift as much weight as he does, but they don't want the pain. So you want the gain of becoming a great diagnostic or interventional radiologist, you got to go through the pain of dealing with physics. Audience response. So again, questions are integrated into these lectures so you can kind of quasi-participate, stay awake, at least click on something. Use of poll everywhere online or live if I'm giving this lecture live. And check that YouTube description for the link to the poll everywhere quiz. Here is the said link. What should I do? So now to get into the nitty-gritty and start teaching physics. So here's what I recommend for my residents do. First years, I would say do the RSNA modules, you know, go through this lecture series, get the basics of physics foundation down. Branton Helms has a section on image acquisition. Get that stuff, very basics down. Go through our recommended module course, which is required for our residents. Go through the RSNA modules and attend physics lectures. Second year, a lot of radiology residents really spend a lot of time taking call. So go to what lectures you can, especially ones which you feel are beneficial clinically, like the artifacts lectures, or maybe rewatch the artifacts videos. Maybe think about purchasing a review book. Most people get Crack the Core nowadays, seems to be the most popular one, and start to highlight and go through that. Maybe if you're someone that likes to do questions, do a lot of questions. Really, third year in preparation for the core exam, that's where I tell people they need to really focus on whatever review book they find the best. I used a Huda review book, which is starting to become outdated. Some people use Crack the Core. A lot of people use that Physics War Machine. Talk to your more senior residents to find the best resources out there for you, and then do lots and lots of questions to practice your knowledge application. You know, universally, I think Rad Primer has great questions. There's lots of banks out there. Some of them are even free online, but do as many as you possibly can. Fourth year, just sit back, have a cocktail, and forget about all the physics you learned. Again, I would say by and large right now, which, you know, I'm doing this late in 2020, the year that was full of nothing but disappointment. But right now, radiologic physics, most people learn it at my institution anyway through Crack the Core and review it. So Crack the Core, Physics War Machine, these are the most commonly used preparatory materials for the core exam in radiology now, although there's lots of good materials out there. So again, check with your senior residents. I particularly like the Walter Huda book, which may be on an even 5th or more edition now. I also used Bushberg kind of sparingly. So if there was a concept that I just couldn't understand, I had this Essential Physics of Medical Imaging. This is a huge book. I don't think many people actually read it through and through. However, there's certain MRI concepts that I just couldn't understand any other way. I would go in and read about, and really outlines them in a very thorough manner. So consider using this as a reference. Nikoloff has a radiology review physics book. This is a little outdated now, but a lot of it was kind of question and answer, which I liked. Again, physics for the radiology core exam, Physics War Machine, the RSNA modules online are all excellent. And again, you know, Kevlar, Board Vitals, Rock the Boards, Rad Primer, all sorts of different question banks that you can use. And really, it's important not only to have the concepts down, but also to test your knowledge application. Disclaimer. So I'm not a doctor, but I did stay at a Holiday Inn Express last night. No, I am a doctor, but I am not a physicist. Why did I do these lectures? Well, because absolutely no one else would volunteer to. So don't complain to me about how crappy my physics knowledge is. I successfully got through my physics boards, did quite well on them. Many of my residents have done quite well. So this is the best you get. All right, this is the basics of atoms, units, and radiation interaction. Here are some suggested references for what you can do accompanying RSNA modules, as well as references for some commonly used texts. All right, we got to go back to the structure of an atom. What makes up an atom? Well, you have a nucleus, which is right there in the central part of the atom, where you have protons, which are positively charged, and neutrons, which are neutral. And they're surrounded by these electron shells of orbiting electrons. And these orbiting electrons are arranged in different energy levels. So you have energy levels which are very closely bound to the nucleus. In this case, it would be like the K-shell electrons. And you have electrons that are more loosely bound, more peripheral in the electron orbital sphere, for example, the N electrons in this diagram. The maximum number of electrons per shell can be mathematically calculated at 2n squared. So if K is the first one, 2 times 1 squared is just 2, and then in the L shell it would be 8, M you get up to 18. So progressively there's more electrons peripherally the further out you get from the nucleus. Lower shell electrons are bound more tightly to the nucleus, so their binding energy is higher. Binding energy is inversely proportional to the square of the distance. So the closer that an electron gets to the nucleus, it inversely gets more and more bound to that. I should say that the closer that it is to the nucleus, it kind of exponentially gets stronger in attachment, or a higher binding energy. But what happens if you take some energy and exert it upon an atom? This is really the basic foundation of how a lot of X-ray imaging and even gamma ray imaging kind of occurs within radiology. So basically we take some form of energy and exert it upon a specific atom to try and get a desired effect. All right, first question to keep you awake. The above diagram shows a tungsten atom, energy released from an electron that moves from the K shell to the L shell would be which of the following? You can either pause it now or take some more time. Here are your answer choices. The correct answer is 58.5 keV. And if I go back, if you just look at the 69.5 keV electron in the K shell, if it moves down to the L shell and assumes an energy of 11 keV, and this is kind of tricky because these are measured in negative kiloelectron volts, the difference there is 58.5. So when energy is exerted upon an atom, if it's greater than the electron binding energy, what happens is an electron from the atom is kicked out and the atom undergoes ionization, or actually changes charge. If that energy exerted upon the atom is less than the binding energy, that electron just jumps up a level. So here's a diagram in the left lower hand corner where you can see energy is exerted upon an atom. It's greater than the electron binding energy, creates an ionizing particle, which is a negatively charged electron, which is free from the now positive ion of that prior atom. If the energy is insufficient to kick that electron out, then that electron will just jump up a level. So it will assume that energy and go from like the K shell to, say, the M shell in this example. So once an electron is excited, what's going to happen? So in this example, a photon, or just a form of energy, is exerted upon the ground state of an atom. It's absorbed, and then that atom goes into an excited state where the electron hasn't been released, but it's excited. What can happen is that energy that went into that excited state, or that excited electron, can be transformed into an X-ray. This typically happens with heavy elements, which is why a lot of heavy elements are used for X-ray production in a diagnostic radiology X-ray machine. Alternatively, an Auger electron could also be formed, which is more typical of light elements that aren't used for this purpose. So again, you have incident electron energy. It's not an incident energy which just causes a higher energy secondary electron. It doesn't have enough to kick it out and create ionization. What then happens is, as it falls back to its baseline, tighter bound shell, it can release a characteristic X-ray, or it could release an Auger electron. Obviously, we're more interested in radiology in the metals that create characteristic X-rays. All right, next question. Which of the following heavy elements preferentially release characteristic X-rays when energized and hence is commonly used in clinical X-ray tubes? You can pause now if you need more time. The correct answer is tungsten. All right, tungsten is used. We'll go over it in more detail when we go through all these image receptors and anodes and cathodes, but tungsten is a very commonly used element in machines which are designed to generate X-rays. So nomenclature is the death of us all. We have to know it, though. We have to be able to talk about it. So a lot of times, like if you're on a nuclear medicine rotation, people will talk about Tech 99 or Tech 99M. And what they're referring to is basically the nomenclature of different parts of the atom. So if we take a general element X and we talk about A, that's the mass number. A is the mass number, which is really the protons and neutrons. Z is the proton number, and then N is the neutron number. And as you can see here, if you know any two of these, you can compute or calculate the third one. X is just the chemical element, and the chemical element, if you go back to the 8th grade science class that you always knew you'd need someday, the chemical element is derived from the proton number. So if you know the element, technesium, then you know the proton number, or Z. So technetium by default has a proton number of 43. Then, if you know the A, or the mass number, you can back calculate how many neutrons are there, because you have to, it has to be, 99 minus 43 equals 56, for example. So frequently, these different isotopes will just be shortened to Tech 99. Because if you know that it's Tech 99, you know by default how many protons are there, because technetium has 43. And you know by default that, if the atomic mass is 99, it has to have 56 neutrons. So Tech 99 is what we use in shorthand, but really in longhand you can figure out what A, Z, and N are given X material. The configuration of the nucleus. So the ground state is like the lowest energy, most stable state. It's the Toyota Camry of atomic states, right? Nice and boring toaster car. Anything above the ground state is you get real excited. So if the nucleus is excited, it's kind of like a sports car, like a Lamborghini or a Ferrari or something. Most excited states are too short-lived and unstable to be useful to imaging. They're some of them are only milliseconds in their duration. However, there are a few nuclei which have excited states that have relatively long half-times, and oftentimes they will be called metastable, or M. So if you talk about technetium 99M, you're specifically talking about a excited state which is metastable, and it can last sometimes for hours, which makes it useful for medical imaging. More boring nomenclature. So you really have to be cognizant of what the difference between an isotope, an isomer, an isotone, and an isobar is. It would be a shame if you failed diagnostic radiology core exam because you couldn't define these four things. So an isotope is the same element. By that fact, it has the same number of protons, but it has a different number of neutrons and therefore a different mass number. An isomer is the same element with the same number of protons and the same number of neutrons, but it's just in a different energy state. An isotone is the same number of neutrons, but it's a different element. And an isobar is the same mass, but it's a different element. So it has a different number of protons because it's not the same element. Which of the following is a correct pairing of a set of isotopes used in nuclear medicine? Pause now if you need more time. The correct answer is I-123 and I-131. So if you go back, it wants isotopes. Isotopes are the same element, the same number of protons, but a different mass unit, different number of neutrons, like I-123 and I-131. The line of stability. So, I'm not talking about the line of stability in Korea along the 38th parallel. What I'm talking about is the repulsion of nucleons. So there's something called the nuclear force. So if you think about a nucleus, you have all these positively charged protons. So you would think that, positive, if you take two batteries and you take the positive poles and try and push them together, you're going to get resistance. Positive charges repel each other. However, there's something called the nuclear force which hold things together. And these are kind of in direct opposition to each other. So as you get more and more protons, you have more and more charge trying to force these protons apart and the nuclei apart, and that's in direct, opposition to the nuclear force, which is trying to keep everything together. If you graph out elements according to how heavy they are, you'll find that the atomic numbers less than 40 tend to be very stable when they have an even number of protons and neutrons. So if you look at this graph and you go up to 20, an element at 20 is going to be very stable when it has the same number of protons and neutrons. Above that, heavier atoms are actually more stable when they have more neutrons, and they need more neutrons to effectively counterbalance the positive repulsion amongst protons with that nuclear force. Really heavy nuclides are essentially all unstable and tend to break apart or undergo different forms of nuclear decay, which we'll get into. But just know heavier atoms, more stable with more neutrons. Lighter atoms, especially less than 40, tend to be stable with an even number of protons and neutrons. Okay, I'm unstable, so how do I decay? Nuclear decay. So the goal is to maintain a stable N to Z ratio along that line of stability. To keep stable, a nucleus can do a couple of things. It can change a neutron to a proton, or it can change a proton to a neutron to try and stay along that line of stability. It can emit an alpha particle, we'll get into that. And it can, finally just break into two completely different lighter nuclei. Excess energy generated in these nuclear decay processes is released in the form of gamma photons. Gamma photons are especially important to nuclear medicine, or the energy is passed along to orbiting electrons. Why is that neat? Well, here's a picture of a gamma camera, right? So if we put something that's decaying, and as part of that decay it's forming gamma photons, we can take pictures of that, see where they go, diagnose people with varying degrees of disease, and help get them treated and help all of humanity, save the world, that kind of stuff. All right, so here's a summary for decay processes. If you have a parent and it's neutron poor, it tends to undergo electron capture. If it's neutron poor, it can also undergo positron decay. If it's neutron rich, it tends to undergo beta decay. All of those daughter particles that are created through electron capture, positron decay, beta decay, tend to form daughter products which are unstable. They then undergo decays which can oftentimes emit gamma rays or undergo internal conversions of electrons that eventually release X-rays. The laws of conservation. So as we go through all these decay processes, just remember that mass has to be preserved with all decay and the charge has to be preserved. So as you try and figure these things out, like maybe you get a multiple choice question where you have one side of the equation and you have to figure out the other side of the equation. You have to know that 1, mass is always preserved, and 2, charge is always preserved. So here's an example of gamma decay. So gamma decay, if you look up here, gamma decay, basically the proton number stays the same, the atomic mass stays the same, the element stays the same, it's just a gamma ray is emitted. So a gamma ray is emitted and everything else kind of stays the same. So which of the following is correct for the most commonly used gamma decay example in nuclear medicine? Feel free to pause now if you need more time. The correct answer is technetium-99m to Tech-99 and a 140 keV gamma ray. So why is this useful? Well, 1, technetium-99m tends to be stable and last a long time, so it can be transported from a nuclear pharmacy to be injected, to be biodistributed and then imaged, for example, in like a bone scan. And we have machines called gamma detectors or, some people used to call them like anger cameras, which can detect 140 keV gamma rays and see where they went in the body. So it's very useful. All right, internal conversion decay. So what happens with internal conversion decay? That's where a nucleus has energy, and it imparts its energy onto an orbiting electron, kicking it out. So a nucleus has excess energy. To stay along that zone of stability, it takes that energy, imparts it on an orbiting electron, kicking it out, and then what happens is that an outer shell electron will fall down, and either an X-ray or an Auger electron is released. So if you think about it, energy imparted onto electron gets kicked out, one of these outer orbiting shells falls in, and an X-ray is released as a result of that energy that's gained by going from the outer orbital shell to the inner, more tightly bound shell. Beta decay, or I-131, is an example of beta decay. So beta decay, a neutron will change into a proton and an electron and an antineutrino. So you have I-131, for example. To stay stable, it's going to change one of its neutrons into a proton and an electron, so positive and negatively charged, so charge is preserved, and also this accompanying particle called an antineutrino. In this example, carbon actually changes to nitrogen, because remember, we're changing the number of protons. You're gaining a proton going from 6 to 7, so you're actually changing the element. So carbon 15 here is changing to nitron and an antineutrino. Since the number of protons change, that element does in fact change during a beta decay process. All right, so what is an antineutrino? I'll pause here to give you time to answer. So we'll age people to see who grew up in the 1980s like myself. If you know who the Super Mario Brothers or the Ninja Turtles and Shredder are, maybe I spent a significant portion of my grade school life watching those things, maybe even a little bit of high school and college too. I'm not saying I was a loser, but I definitely wasn't a winner. But what is an antineutrino? It's just an antiparticle of a neutrino that carries energy but neither has mass nor charge. That is literally all I know about a antineutrino, and I'm a very successful diagnostic radiologist, so I don't think you need to know much more than that. All right, beta decay. So the child nucleus in this type of decay is unstable, and oftentimes it will then undergo decay itself, sometimes in the form of a gamma ray. And if you think about molybdenum, so that's the classic example that people like to use for beta decay. So molybdenum 99 undergoes beta decay because it's inherently unstable, goes to Tech 99M plus an electron, and then that Tech 99M is unstable in and of itself, and that tends to release a gamma ray, which we can use for imaging. So it takes a couple steps from what the nuclear pharmacy uses, which is like a molybdenum generator, to get all the way down to the gamma ray that we use. It undergoes beta decay and also gamma decay of the daughter product. All right, beta plus decay. So this is annihilation and positron emission. So what happens here is a proton actually changes to a neutron. So the element actually changes what it is because the number of protons is changing. And a positron and a neutrino are released. What's the example of this? Well, it would be like F18 fluorodeoxyglucose, which is what we use for PET scans. So you have an unstable parent, a proton decays into a neutron in the nucleus, and a positron and a neutrino are emitted, and that positron eventually undergoes decay into two 511 keV photons, which can be imaged in a PET detector, which when we go through the PET detector lecture, you will learn how we image those anti-parallel 511 keV photons to create a PET CT image. All right, next question. F18 in F18 FDG undergoes positron decay, the fundamental basis of positron emission tomography. What does it form? Pause now if you need more time. The correct answer is oxygen 18. All right, what happens to the poor positron? So the positrons interact with electrons, annihilate, and form two 511 keV electrons that are exactly 180 degrees apart. And this is a kind of a spec model of a PET camera where there's detectors. The detectors are 180 keV apart. If they detect a photon coming at the similar times or within a certain time frame, it's considered a count event. It's a lot more complicated than that, or a coincident event. And then it's used to recreate an image. Again, during the PET-CT portion of this lecture series, you'll go into a lot more detail of that process. Decay by electron capture. All right, so electron capture is another way for an unstable atom to decay. This is where the nucleus wants to make a proton into a neutron, so it just takes an orbiting electron and it does it. The net effect is similar to a beta plus decay. Light elements tend to undergo positron decay. Heavy elements tend to undergo electron capture. I always remember that as a big heavy person just can do what they want because they're a big heavy person. I don't know if that helps you go with it. Examples in nuclear medicine of electron capture. So gallium, indium, I-123 daughter products are created through electron capture. Interestingly, then those daughter products oftentimes release gamma rays undergoing gamma decay, which is what we use to image them. But initially, gallium, indium, I-123 undergo decay by electron capture. The final form of decay isn't real common. Alpha decay and nuclear fission. So alpha decay is where two protons and two neutrons are just ejected out of a nucleus. So a helium nucleus is released from an unstable nucleus. The main example I have from medicine where this occurs is in radium-223. This is a treatment, trade name Xofigo. We use it in nuclear medicine to treat osseous metastases because if you look at the periodic table of elements, radium is right there by calcium and behaves similar to calcium, so it will go to sites of bone turnover, like in a prostate cancer patient with multifocal metastatic disease in their skeleton. Alpha decay is very powerful, but it has no penetration, so that's the whole purpose of, or reason why radium-223 works, is because it delivers all of its decay energy locally within millimeters around where it lands, which is in bone. That's its biodistribution. Again, kind of a calcium mimic. It doesn't go to other places, so it doesn't have the radiation side effects because it doesn't end up landing in like your, mucosal surfaces of your mouth or something like that. Fission is a heavy nucleus which decays into two lighter nuclei and releases energy. This is a nuclear bomb. So it's not directly used in medicine that I know of. All right, quantitative nuclear decay. So we've gone through the descriptive ways of how a nucleus can decay. Now we have to talk about quantification of it. The international unit for nuclear decay is the becquerel. That's 1 decay per second. We're Americans, so we've got to be different than everyone else, just like gallons and meters and all that stuff. I don't know why we're special, but we are. And the American system uses a Curie. So a Curie is defined as 3.7 times 10 to the 10th decays per second. So 1 millicurie is equal to 37 megabecquerel. Most nuclear departments in the States report our doses in terms of curies. Most nuclear medicine research publications and international places tend to use becquerels. You can get on Google and do an easy conversion calculator if you ever need to. Quantitative nuclear decay. So there are formulas where you can calculate this, and when I was a resident, we would actually have to figure these mathematical formulas out. I think that's kind of a waste of time, but you should understand the concepts. So there are formulas to calculate how fast or how much something will decay, and each element has its own individual decay constant. In vivo, there are both physical half-life things going on and biological half-life things going on that are important in terms of patient dose and how long it lasts in the body. So not only, if we inject a radiopharmaceutical, let's just say like technetium-99m MDP for a bone scan, there are two decay processes. One, there's the physical decay of that, where 99M is going down to Tech 99 and releasing a gamma photon. So that's causing elimination of Tech 99M. But also there's a biological half-life. Your kidneys are taking this radiopharmaceutical up and you're urinating it out, which is getting rid of it as well. And you can calculate a decay constant by taking those both into effect. Children are complicated. So I put this picture of my kids in there because they all look smiling and happily, and you wouldn't have any idea how 3 such beautiful kids could cause my life to be so miserable. But no, children are complicated. So calculating decay is complex because the daughter products that are formed by these decaying atoms are oftentimes unstable and decaying themselves. And usually what happens is in vivo and in vitro, the daughter products and the main basic atom that we're talking about form an equilibrium. And there's a couple different equilibrium types. So secular equilibrium, that's where the decay of the parent is so long that the child's decay is negligible. So the example of this would be radon-226, which is frequently found in basements in Nebraska, turning to lead. So if you have secular decay, the parent half-life is so long that really any decay by the child products is negligible. Transient decay, that's where the parent half-life is greater than the child, but not very long in and of itself. So an example would be molybdenum-99 used in nuclear pharmacy to generate Tech 99M. So the parent half-life is greater than the child, but it's not very long, so you reach kind of a transient decay. For example, molybdenum-99 has a 66-hour half-life, Tech 99M is a 6-hour half-life. And then you have no equilibrium. So this would be like secular decay, transient decay, and then no equilibrium. That's where the child just outlives the parent, kind of how hopefully nature works for most of us, where the child is eventually completely replaces the parent. All right, at nuclear pharmacies, molybdenum-99 generators are eluted every 24 hours, not sooner and not much later, to obtain technetium-99M for nuclear medicine studies. Why is that? Feel free to pause now to take time to think. Contrary to popular belief, nuclear medicine technologists do not take their afternoons off. The correct answer is molybdenum-99 and Tech 99M decay via a transient equilibrium, and the peak of their equilibrium time is about 24 hours. So if you go back and look at like a transient equilibrium, they're going to be hitting that peak at about 24 hours. So really there's no benefit in letting it go forever. They've reached an equilibrium state. You might as well elute off the Tech 99M and then have it regenerate 24 hours later. It'll hit its peak again, and you elute it off again. All right, now we're going to cover some more boring stuff from RSNA Module number 2, Radiation Measurements in Units. I usually like to put a little break, I call them mental health breaks in my talks about something more interesting than what I'm talking about, especially if I'm giving a rather boring talk. So I put this in here about Marie Curie. Feel free to skip over it if you're boring. But Marie Curie, so she was born in 1867. She was the first European woman to get a PhD in physics, first person ever to win 2 Nobel Prizes, one in chemistry, one in physics, pioneer in early nuclear research involving polonium and radium. She's often shown with her husband Pierre, like in this picture here, even though he really didn't do anything nearly as important as she did. And that all sounds boring, right? She's shown as an old person in a boring lab. But if you have a chance to read a book about her or see a documentary, she really led a fascinating life. I like this picture better of her as a fierce young woman. So, it was illegal for women to get higher educational mathematic degrees and scientific degrees at the time. So she had to go to an illegal underground night school run by young Polish academics for education. To access this, she lived with her uncle for a period of time. He wrote back to her parents that she is very independent, therefore thought, though you named me her official guardian, she not only shows me little respect, but also refuses to listen. She cares about my authority about as much as she would care about a torn shoe. That really describes my daughter in detail also, so I'm expecting very big things out of my Lizzie. During World War I, she put together these things called Petite Curies. This was basically a mobile X-ray unit used to help triage soldiers in the field for bullet fragments and broken bones. She went on vacations with Einstein, so she was kind of a celebrity of her day. And to show that the world didn't start with TMZ.com, she actually had an affair with one of her husband's former students after her husband passed away. And it was so scandalous that the Nobel Committee formally requested she not come to receive her second prize in person, but she politely declined and showed up for the award. Just deservedly so. She deserved the award, showed up and got it. She was a martyr for science, died of aplastic anemia, likely secondary to those high exposures that she had around World War I. It was said that she used to be cold and would put vials of radium in her lab coat to help keep her warm. And obviously that's a big mistake. All right. To get into the nitty-gritty of the International System of Units, there are 7 base units. All measures of radiation are derived from these base units. Again, I'm not going to go into this in too much detail, but there are lots of things in these international units which are applicable to medicine and radiology in particular. So hertz, you have to know about hertz or frequency, sound unit measurement for ultrasound. You have to know about Tesla's magnetic field strength. This is a unit for MRI. You have to know about lux or illuminance. This is how in our reading rooms we measure compliance for ACR standards of reading. Like, why do we read in the dark? Well, the American College of Radiology says we do it better, and they even have guidelines for how dark it has to be. Gray is absorbed dose. That is useful in terms of relaying doses of radiation exposed to a patient. A sievert is the equivalent or effective dose. We'll get into that. Becquerel, we already covered. It's a radioactive decay activity unit. Historical units are still commonly used. So like the electron volt, the SI unit would be the joule. But most of the time when we talk about like a CT settings, we'll talk about keV or kiloelectron volts. An electron volt is just the energy an electron would acquire by moving through a potential of 1 volt. Most X-ray energies are in the range of 20 to 120 keV, and Tech 99M gamma rays are about 140 keVs. So in terms of what we image, it's usually 20 to 140-ish on average. The mass of an electron is 511 keVs. So if you think back to, that's kind of what a positron is 2 511 keV photons going in opposite directions. So that's not a coincidence, right? So if you look at it, most of our diagnostic imaging has detected things between 20 to 140 kiloelectron volts. An exception would be like a PET scanner, which is detecting things at 511 keV. So how do we measure radiation? It's usually based on the amount of air ionization that given radiation produces. Historical unit is the Roentgen. How do we measure it? Well, air ionization, and these will be covered in more detail in the radiation biology and safety lectures, but the basic way that you can measure radiation is with a Geiger counter. That's that pancake probe on a Geiger counter to your left, or a dose calibrator on your right, where you take a dose of a radiopharmaceutical, put it in the calibrator, and get spit out a dose. Air ionization, though, how much ions are being made in the air around a radioactive substance, isn't very helpful in terms of, elucidating a radiation effect on humans. So the concept of radiation dose was developed, and that really takes into consideration energy absorbed per unit mass. Originally, this unit was the rad. It's now been replaced by the gray, although a lot of radiologists will still talk in terms of rads. A lot of physicists will as well. But gray is what we really should be using, and that's just 1 joule per kilogram of tissue, for example. All right, the average American gets what radiation dose from background exposures every year? Pause now if you need more time. This is where you may sound or feel very ignorant if you guess and have no idea what to say, and you actually guess that the average American gets a lethal dose of radiation, which obviously is not true. So the correct answer for the average dose is 3 milligray. If you got 5 gray, you would be dead. 3 milligray is the correct dose for average annual environmental exposure. So dose and volume. So if you think about, dose, it's radiation per kilogram, so it really depends on volume, right? So the dose here is the same in both cases because it's per unit volume. So if you expose someone a larger volume, the dose per volume tends to stay the same. If you expose, regardless of whether you expose 1 centimeter of body to a dose of 5 millicuries, or if you expose 100 centimeters of body to 5 millicuries, the radiation dose to any given tissue is the same. However, the overall risk is higher for the person on the left because they have more tissue that was exposed. So there's a lot of really complex and competing things going on with radiation dose when you talk about it. In addition to that, some tissues are much more radiosensitive than others. So a dose could be the same. The overall amount of tissue could be the same, but the given tissue type could be different and someone could have a higher risk. So in essence, it's very complex. There are a couple units as we delve deeper into the rabbit hole that is radiation nomenclature that you have to know about. KERMA is just a way for physicists to intimidate you by using a fancy word that you don't know what it means. So KERMA is kinetic energy released in matter. Oftentimes this measurement is done in air, so like the KERMA in air, or air KERMA is frequently used. This measurement is used to just assess for how much radiation is present. An example would be using a Geiger counter in air to get the air KERMA. The unit of KERMA is the gray. Not all doses are created equal. Different radiation types like gamma, beta, alpha, etc. have different effects on tissues, and the concept of equivalent dose was made to account for that. So this modifies for the given radiation exposure with a radiation weighting factor. So the equivalent dose takes into account not just how much radiation there is in air, but also the type of it. And it introduces a new unit called the sievert. So equivalent dose equals the radiation dose times that radiation weighting factor. What's super confusing, or at least it was for me going through, is that the equivalent dose oftentimes is the same as the radiation dose. So gray is oftentimes interchangeable with sievert. And why is that? Because the weighting factor for radiation types used commonly in medical imaging, like X-rays and gamma rays, just so happen to be 1. So the equivalent dose is oftentimes, especially when you're dealing with X-rays and gamma rays, the same as the radiation dose. Equivalent dose equals the dose times the weighting factor. If that weighting factor is 1, it's going to be the same. Thus, for medical imaging, usually gray and sieverts are interchangeable, which a lot of people get kind of sloppy and use them interchangeably, which you really shouldn't, but just be aware that happens. But that is not all. Oh no, that is not all, as the Dr. Seuss book would say. Equivalent dose has accounted for radiation type, but we also need to account for the type of tissue exposed. As I mentioned earlier, different tissues have different radiosensitivities. So the effective dose, unit sieverts, accounts for this by multiplying the equivalent dose times a tissue factor. So we've gone from radiation dose to equivalent dose, which takes into account the type of radiation, to effective dose, which takes into account the type of radiation and the type of tissue being exposed. The effective dose is just the sum of that weighting factor times all the individual organ doses. So if you have 2 different types of organs being exposed, the effective dose is the dose to organ 1 times its given weighting factor, plus the dose to organ 2 plus its weighting factor. And you add all those up and you have your overall effective dose. The weighting factors for different tissues are here. If you think about it, things that kind of replicate rapidly tend to have higher weighting factors. So like bone surface is relatively radio resistant versus like marrow and gonads, things which are high risk, or like mucosal surfaces have higher rating factors. People are oftentimes concerned about chest CT and breast cancer risk because breast is a relatively radiosensitive organ. So just be aware of these. Again, if you look at these radiosensitive organs, things like the gonads, red marrow, mucosal surfaces, oftentimes are preferentially susceptible to radiation effects. So what dose do I use? For every CT, the scanner actually generates a number for you, and it's not the any of the things I've already said: absorbed dose, equivalent dose, effective dose. It's the DLP. So every scanner, after every scan, gives you a dose length product. What this is it takes the estimated effective dose and generally via conversion factor gives us what we report as the effective dose. So it's used in research and individual applications, although in theory it's best generalized just to a larger group. So if you have effective dose conversion factors, like for a head CT, for the head and neck, for the chest, for the abdomen and pelvis, a lot of times the chest, abdomen, and pelvis has a whole bunch of different types of tissues, right, throughout the chest, abdomen, and pelvis. So just an effective dose conversion factor was made. It happens to be 0.015 to account for the average kind of risk that those tissues represent. So if you look at your average report on a CT scan, it'll give you the total exam DLP. Let's say this was for a chest, so you take the chest weighting factor, times it by your dose length product, and then you get a magical effective dose. Controversies. How accurate is this? Should we report DLP and effective dose on our CTs? Many places are going towards reporting this on every CT scan, every radiologic study, even every fluoroscopy exam. I don't know how accurate these numbers really are in real life. In real life, in vivo is always a lot more discrepant than in vitro models. Plus, no one really knows what an effective dose, let's say of 1.5 millisieverts, what really does that convey to you in terms of cancer risk? Very hard to differentiate amongst individuals what that kind of means. Obviously, it's more important than kids and older people, more important in healthy people than in people with terminal illnesses. But a lot of quality standards in radiology now revolve around trying to get radiation doses down, because less radiation is better as long as you can maintain diagnostic quality. So a lot of places will report their DLP and effective doses on their CTs. Next question: which of the following concerning effective dose in a body is false? Pause if you need more time. Correct answer is directly measured with an ionization chamber. So if you go back to these, which is false, expresses mean radiation energy deposited per unit of mass. Well, that's exactly what effective dose is. Is related to radiation-induced biological effects. Well, of course it is. It is reported in units of sieverts. That's correct. You can't directly measure it with an ionization chamber. That would measure air kerma or just radiation in air, right? So it does not measure effective dose. All right, dose is the energy absorbed per unit mass in gray. Equivalent dose factors in the type of radiation, change unit to sievert. Effective dose factors in type of tissue, sievert. To get the effective dose for a CT, you take your DLP, which is generated from the scanner, dose length product, and multiply it by a tissue weighting factor, which you can look up in tables on the internet. Equivalent dose equals the weighting factor times the dose. Effective dose is the sum of the organ dose times all those tissue factors. All right, you can go through this sample CT calculation if you want to. I don't think it's important for the core exam to really be able to do these calculations, although to have their concepts down and knowing if you change like the length of the scan, what's that going to do to your DLP, etc., is kind of important knowledge to have, although I don't think specific calculations will be needed. All right, which of the following takes into account both the type of radiation and the type of tissue involved? Here's the ultimate end game challenge to see if you understand all this stuff. I'm going to pause now. Effective dose. Effective dose takes into account both the type of tissue and the type of radiation. All right, what is the average effective dose in millisieverts for the following? CT chest, mammogram, chest x-ray, or PET CT? Pause now. So the correct answer was 8.7.0 0.02 and 14. So you don't have to memorize these, but what I would tell you to do is just think about them, right? So what's the highest dose? So a PET CT scan is going to be the highest dose thing here, right? You're irradiating the whole body from head to mid-thigh. You're doing a CT scan, and you're giving a F18 irradiation dose. So if you're going to pick the highest one, it's got to be that. So it's got to be 14 here. So you can essentially eliminate all these other possibilities and go with this. And then intuitively, if you look at it, a CT scan of the chest, CT scans generally have much more radiation than plain films like a chest x-ray or a mammogram. So it's got to be 14 here and 8 here. And it makes the answer actually pretty easy to derive. All right, units of radioactive decay. So we have a Curie, that's the number of decays per second of 1 gram of radium. That's 3.7 times 10 to the 10 disintegrations per second. Becquerel is 1 disintegration per second. And there's numerous online calculators that you can use. Ultrasound related units, we'll get into all these in more details in the modality specific lectures. A Pascal is a unit of pressure. It's defined as well, you can read that there. Atmospheric pressure is about 101 kilopascals, just to put it into perspective for you. A Rayel is a unit of acoustic impedance. A decibel is a unit measuring signal attenuation for sound and ultrasound. We'll get into those in more detail in the ultrasound videos. CT units, so a Hounsfield units is just a CTs are a map of linear attenuation coefficients of the thing being imaged. If you don't understand what that means, it's okay. Again, there'll be dedicated CT lectures. Easier to understand these coefficients when ranged on a scale. So like artificially, air is assigned a Hounsfield unit of -1,000, water is 0, and things like soft tissue would be like 60 to 70. Liver 40 to 60, fat is usually -50 to -100. Again, these will be covered in much greater detail in the CT dedicated videos. But you can use them. So like if you have a pericardial effusion, you can measure the Hounsfield units within the pericardial effusion, and in this case it's 36, which is more than simple fluid, and you can diagnose this person with hemopericardium. You can also diagnose people with like a lipid-rich benign adrenal adenoma because the average CT density is 0.7 Hounsfield units. So these units are actually quite useful in clinical practice. Here you have a cyst, which is not really a cyst. It's got a Hounsfield unit analysis of 101, so that's actually an enhancing solid renal mass. MRI units, Tesla, it's a unit for magnetic field strength. Gauss is used to measure small magnetic fields. So like 1 Tesla would be 10,000 Gauss. Tesla is generally used for like a large magnet. Usually common clinical magnets would be like 1.5 Tesla or 3 Tesla. Gauss is used for smaller units, and those are typically used for like warnings. Like when you go into a CT scanner, there'll be a 5 Gauss line where there are certain restrictions, take stuff out of your pockets, no loose metal, etc., before you cross that line and enter into that magnetic field, which gradually increases the closer you get to the magnet. There are light-related units as well. The candela is the basic unit of luminous intensity. Luminance is just luminous intensity divided by square meters. So your average PACS monitor luminance is about 500 candela per meter squared. Mammography monitors have to have a higher luminance to meet regulatory guidelines, up to 3,000. That's why mammography monitors are so much more expensive than an average PACS monitor. You really need that to see optimally small calcifications, which can be a sign of breast cancer. Lux is the unit for luminance. It's the amount of light falling on a given surface. This interferes with the eye's ability to appreciate contrast, which is why we have to read in the dark. So does any of this matter? Yes, there are lots of studies out there showing that if you try and interpret something subtle, like a wrist radiograph or a scaphoid fracture, you'll miss subtle findings and lose subtle contrast differences in radiographs if you read with the lights on. So that's why we work in the dark. All right, last question. What is the ACR guideline for optimal ambient light settings when reading digital mammography? The correct answer is 20 to 45 lux. Studies on ambient light have shown deleterious performance on interpretation at higher levels. So that's why we do it in the dark. All right, so that terminates the first lecture. Thank you very much for watching along, and look for more videos to come.